Good morning to all. Today I am recording the video lesson on simple stresses and strains. So this is the lesson for the day 10. Today we are going to discuss about the volumetric strain, and we are having the formulas for the volumetric strain for a structural bar and for the rectangular bar also. And first we will come to know the formulas to find out the volumetric strain. Then we will solve some examples so that we have the clear concept on the volumetric strain. So now we will proceed to the lesson through PPTs. So I am sharing the PPT. So our lesson is a simple stress and strains. In that today we are going to discuss about the volumetric strain. So in the previous classes we have defined the stress, strain, and modulus of velocity, and also three elastic constants, namely the Young's modulus, modulus of rigidity, Buck modulus, that is ECK, and also the Poisson's ratio. And also we know the basic equations to find out the stress, strain, modulus of velocity, and also we know the relation between the modulus of velocities and modulus of rigidity, and also the Buck modulus. Anyhow, we have to call back that formulas because the knowledge of these formulas is very essential to solve the problems and to study the volumetric strain. First of all, we know that the stress F is equal to force by area, so F is equal to P by A, and also the strain E is equal to, that is called longitudinal strain, delta L by L, and we also have the lateral strain. Lateral strain is nothing but the change in lateral dimension to the original dimension. That may be equal to delta D by dA or delta B by B or delta T by T when the force applied along the lengthwise. And we also have the one of the important ratio, the important ratio, that is called as the Poisson's ratio. That is nothing but the ratio of the lateral strain to the linear strain of any body, and it bears a constant ratio, and it will remain constant for that material. Next, we also have the Young's modulus. E is equal to stress by strain, that is F by E, and that is also equal to P into L by A into E. So the stress by strain is equal to modulus of, so P into L by A into delta L will give the Young's modulus value. And also we know the delta L value, that is the change in length, that may be elongation or contraction. Delta L is equal to P into L by A into E. And apart from that, we know the relation between the three elastic constants. The first equation is E is equal to 2C into 1 plus 1 by M, and E equal to 3K into 1 minus 2 by M. Here 1 by M is the Poisson's ratio. The next one is here we know the load area of section, modulus of rigidity, C, K the Buck modulus, and 1 by M is the Poisson's ratio. Like this, we got the some basic equations that we have derived and we have learned in the previous lessons. So those are very essential to study the volumetric strain and to solve the problem of this. Now, the objectives of this lesson is to study the volumetric dimensions of bodies of uniform sections under the action of the normal forces, and to find out the volumetric strain and the change in the volume, etc. And we also able to solve some problems on the volumetric strain. Now, we also derived some equations or the relations for the longitudinal strain, lateral strain, and also the volumetric strain. If you recall back those values, now the longitudinal strain E is equal to delta L by L, that is also equal to stress by Young's modulus, that is equal to F by E. The next one is the lateral strain. The lateral strain is equal to change in lateral dimension by the original dimension. So here, whenever a force is applied along the length, that is axially, so the length direction will become the length is the primary direction. The direction along the lengthwise is the primary direction, whereas the other directions which are perpendicular to the length, like width, thickness, or the diameter in case of the circular bar, will be the lateral dimensions, and the strain produced along the lateral dimensions is called as the lateral strain. So generally the lateral strain can be found by the ratio of the change in lateral dimension by original lateral dimension. So here the lateral strain is equal to delta D by D. So this is in case the bar is having the circular direction, circular cross section and having a diameter D. And in case if the bar is having the rectangle cross section with the B and the thickness T, in that case the lateral strain also equal to the delta B by B or delta T by T. and that is also equal to F by ME. Here also 1 by ME is nothing but the Poisson's ratio. Next, the important thing is the volumetric strain. So because our main aim is, so in this class we are going to study about the volumetric strain. So the volumetric strain can be defined as the change in volume by original volume. So here whenever a body is subjected to some forces in either in one direction or either in two or more directions, so the length will increase or it may decrease or increase. The width also may increase or decrease. The thickness also increase or decrease. Even the diameter in case of the circular bar may increase or decrease depending on the nature of the applied force. For example, if a tensile force is applied along the lengthwise, the length will increase, and whereas it will tend to reduce the width and the thickness of the body. Similarly, the tensile force is applied at the ends to a circular bar, then the length will increase, but it will tend to reduce the diameter of the body. And on the other hand, if the compressive forces are applied to the ends of a rectangular bar, then it will reduce the length because contraction will occur. The length will reduce. On the other hand, the width and thickness will tend to increase. Similarly, if the compressive force is applied to a circular bar, the length will reduce. However, the diameter of the bar will tend to increase. So this is the tendency happened when a bar is subjected to some external forces. Similarly, the important thing is the tensile force applied to a bar along the lengthwise will increase the length, but will reduce the other lateral dimensions. They may be the width and thickness or diameter. Therefore, it produces a positive strain along the lengthwise, whereas it produces the negative strain along the lateral dimensions, that is along the width or thickness or along the diameter. So that we must note. And generally, the positive strain can be considered a negative positive one, and the negative strain, that is the contraction, will be taken as a negative one. So here the volumetric strain is nothing but the ratio of the change in volume by original volume, that is equal to F by E into 1 minus 2 into 1 by M. Here 1 by M is the Poisson's ratio. Again, the delta V means the change in volume. The change in volume can be found by the given dimensions. So here the change in volume is the final volume, the difference between the final volume and initial volume. So here the body having the initial dimensions, say length, width and thickness. So LB into T will be the initial volume, and due to the application of the load, the different dimensions may change. So the length will change, width will change, and also the thickness also will change. So the volume with the final dimensions, that is the change in length, width, and thickness, will give the final volume. The difference of the final value minus initial value, or the difference between the final value and initial volume, will give the change in volume. So the ratio of the change in volume by the ratio of the change in volume to initial volume will give the volumetric strain. So here, whenever a rectangular body is subjected to a triaxial forces or stresses, now they are the formulas to find out the volumetric strain. Here, for example, you take the case of a rectangular bar having a length L, width B, and thickness T. It is subjected to the three kind of forces, that is along the lengthwise, along the widthwise, and along the thickness wise. So, and that is also that forces are also acting along the three mutually perpendicular axis, that is x, y, z, and z axis. Here, the volume in this case, the volumetric strain can be found, that is delta V by V is equal to Ex plus Ey plus Ez. Here, Ex means the strain of the, that is the volumetric strain of the body in x direction, that may be lengthwise. And Ey is equal to the volumetric strain of the body in the y direction, that is widthwise. And Ez is the volumetric strain of the body in z direction, that is in the thickness. So by the algebraic sum of the strains in the three mutually perimetric directions will give the total volumetric strain of the body. So that is equal to Ex plus Ey plus Ez. And now coming to the strain, to how to calculate this Ex, that is the strain in x direction. Ex is equal to, we got the formula. Here you know that very simple. Whenever a body is subjected to the tensile force along the lengthwise, it will tend to increase the length. However, it reduces the width and thickness. So here what is happening is, it produces a positive strain in length direction and produces the negative strain in the lateral directions, that is along the widthwise and along the thickness wise. Therefore, the algebraic sum of the strains produced by the force applied in x direction, that is the lengthwise, will give the strain in x direction, that is called as the Ex. Ex is nothing but the, here if you see, we can see that formula. Ex is equal to Fx by E. This is positive, minus Fy by Me minus Fz by Me. Here, the Fx by E means the stress in x direction by modulus of velocity. So here, the stress in x direction is nothing but the what, the force in x direction by the cross-sectional area, that is B into T. So here, when a force applied along the x direction, the cross-sectional area becomes the width into thickness. So Px by B into T will give the stress in x direction. So the stress by modulus of velocity will give the primary strain. And whereas this is the term F by Y ME, because this the force applied along the x direction will also produce lateral strain in y direction. That is in the width wise. But it is not a primary strain, it is a lateral strain. But and one more thing here, what is happening is the due to the application of this force along the x direction, the tensile force along the x direction, the it will tend to reduce the width. Therefore, it produces a negative strain. So that lateral strain will be the negative. Therefore, we have taken the negative side. So therefore, this is called minus Fi by Me. Here minus by E is the linear strain in y direction and multiplied with 1 by M will give the lateral strain. So by Me will give the lateral strain produced by the force applied in x direction. Similarly, the Fz by Me will be the lateral strain produced in thickness in z direction, that is nothing but in the direction of the thickness. So here also Fz by E is the linear strain, but here we are taking the lateral strain. So Fz by E into 1 by M will give the lateral strain. But however, it is also negative because the thickness will tend to reduce due to the application of the tensile force along the x direction. So therefore, this is also negative. So ultimately, the strain in the direction of x, Ex is equal to Fx by E minus F by Me minus Fz by Me. Here we should know that the apex will only the strain in x direction only positive, and the strain in y and z directions are negative. Therefore, we got the negative sign here. So Ex is equal to Fx by E minus Fy by Me minus Fz by Me. Here also one more thing, the Fy, the stress in y direction means the force acting in the y direction by the area of cross section. So that is which is perpendicular to the y. Y means the z and x are perpendicular to the y. Therefore, the cross section will become the length into thickness for Fy. Similarly, the stress Fz. So for the stress Fz, we should take to carry the value of the Fz, the force in z direction by the cross sectional area. And when it is acting along the z direction, the x and y will become the cross sectional area or the perpendicular directions to the z. So Fz is equal to the force in z Pz by L into B, that is the length into width, will give the stress in z direction. And similarly, we have to find out the Ez, so Ey and Ez. The Ey means the strain produced in the direction of the y. Ey is equal to, similarly here, F by y, Fy by E minus Fx by Me minus Fz by Me. That means here the strain produced in the direction of the y due to the application of the force, that is tensile force is positive only in y direction, and it produces the negative strain in y, negative strain in x and z directions. Therefore, we got the two negative signs again, and the strain in the direction of the z, that is Ez. Ez means, so the force applied along the z direction will produce the strain in three directions, in z, x and y. However, the tensile force applied in z direction will produce the positive strain in z direction, whereas it produces the negative strains in x and y directions. And the x and y are the lateral dimensions to that of the x. So it produces a lateral strains in the directions, and they are also negative. Therefore, the strain in the direction of Ez is equal to Fz by E minus Fx by Me minus Fy by Me. Like this, we have to find out the Ex, Ey and Ez, and ultimately the volumetric strain of a body, that is also equal to dV by V is equal to Ex plus Ey plus Ez. Here this is nothing but the algebraic sum. Here some values may be positive, some values may be negative. The algebraic sum of the strains will give the total volumetric strain of the body. Now, with this, now having studied about the formulas, now we will solve some of the problems to have the clear understanding about the volumetric strain. So this is a problem, the first problem given. For a given material, E is equal to 110 kilonewtons per square millimeter, and C is equal to 43 kilonewtons per square millimeter. Find the buck modulus and lateral contraction of the round bar 35 millimeter diameter and 2.5 meter long when stretched by 2.5 meters, 2.5 millimeters. So here what is happening is a round bar is subjected to a compressive force. The force is not given. So here the bar is subjected to only one direction, and the amount of the contraction is given, and E value, C value is given. Then with this, first of all, we have to find out the that is the strain and also the lateral strain, and with the primary strain and lateral strain we can calculate the Poisson's ratio 1 by m, and after that we can calculate the buck modulus as from the given values of the E and C. Now first of all, to solve this problem, the first step is to write down the given data. Here, the modulus of velocity is given as 110 kilonewtons per square millimeter, and the modulus of rigidity is given as 43 kilonewtons per square millimeter. The diameter is given as 35 millimeters, and delta L, here the contraction is given as 2.5 millimeters, and the length of the bar is given as 2.5 meters. That is nothing but the 2.5 into 10 power 3 millimeters, because 1 meter is equal to 1000 millimeters. Now coming to the solution part. Here E is given, C is given. So from this we can get the 1 by m value. So we know that we can recall back the equation. E is equal to 2C into 1 plus 1 by m. Here, and substituting the E value and C value. So here 110 becomes 2 into 43 into 1 plus 1 by m, and 1 plus 1 by m will become the 110 by 2 into 43, and that is equal to 1.28, and 1 by m is equal to 1.28 minus 1. It is equal to 0.28. So the Poisson's ratio 1 by m is equal to 0.28. Now the next step is to find out the buck modulus. So we know the relation between the E and K, because the E value is given, and we know the 1 by m value. So to find out the K value, so we have to use the relation between the E and K. So we know that the K is equal to E by 3 into 1 minus 2 by m. So here 2 by m is nothing but 2 into 1 by m, that is a 2 into Poisson's ratio. So the K is equal to, substituting the values, it becomes 110 by 3 into 1 minus 2 into 0.28. So ultimately it becomes the K is equal to 82 kilonewtons per square millimeter, because we have substituted the E value in Kn per square mm. So we also get the value of K in kilonewtons per square millimeter. So the arrived value per K is equal to 82 kilonewtons per square millimeter, and that is also equal to 0.82 into 10 power 5 newtons per square mm. That is equal to K value. That is the K value. Now the next thing is we have to find out the Poisson's ratio. So we know that very basic equation. The Poisson's ratio 1 by m is equal to lateral strain by linear strain. So here lateral strain will be equal to the Poisson's ratio into linear strain. And the linear strain is nothing but the ratio of the change in length by original length. So lateral strain is equal to 0.28 into delta L by L. So we know the value, all the values of the delta L and also L. So substituting those values, the lateral strain is equal to 0.0000279. So this is the value of lateral strain obtained, and we know that lateral strain is equal to, here it is a circular bar. For a circular bar, it is having a diameter. So the change in diameter by original diameter, that is delta D by D, is equal to the lateral strain. So we got the lateral strain value. So delta D by 35 is equal to 0.000279, and therefore delta D, that is the change in diameter, is equal to 0.000279 into 35. It is equal to 0.0097 millimeters. So this is the required answer for the change in diameter, and its value, the change in diameter is equal to delta D is equal to 0.0097 millimeters. Next, we'll move to the other problem. Here, a cylindrical bar is 20 millimeters in diameter and 1 meter long. During a tensile test, it was found that the longitudinal strain is 4 times the lateral strain. Calculate the modulus of rigidity and buck modulus. If its elastic modulus is 1 into 10 power 5 newtons per square millimeter, find the change in volume when the bar is subjected to a hydrostatic pressure of 100 newtons per square millimeter. So now given data, so this is the given parameters from the problem. The diameter of the bar is D is equal to 20 millimeters. Length L is equal to 1 meter, that is equal to 1000 millimeters. Longitudinal strain is equal to 4 times of the lateral strain. So therefore the ratio of the lateral strain to the longitudinal strain will become the 1 by 4, and that is equal to 0.25. The Poisson's ratio is calculated as 0.25, and the modulus of elasticity for the material is given as 1 into 10 power 5 newtons per square millimeter. So we know the first thing we have to find out the modulus of rigidity. For this, we have to use the equation between the C and E. So we know that E is equal to 2C into 1 plus 1 by M. Here Substituting the values of the E and 1 by M, we will get C is equal to 0.4 into 10 power 5 newtons per square millimeter. And next one is the Buck modulus. So to find out the Buck modulus, we should use the formula between the Buck modulus and Young's modulus. That is K and E. So we also know that E is equal to 3K into 1 minus 2 by M. And substituting the values of the E and 1 by M value, then we can arrive the K value. K is equal to 0.67 into 10 power 5 newtons per square millimeter. Now the next one is we should find out the change in volume. Here we know that the volumetric strain EV is equal to the 100 by 0.6 and 10 power 5. So the change in volume is equal to 100 by 0.67 into 10 power 5 into V. Here V is nothing but the volume of the bar. Because it is a circular bar, the volume will become the 5 by 4 into d square into L. So here it is having a diameter of 10 millimeters and length of 1000 mm. So 5 by 4 into 10 whole square into 1000 will become the volume, and when it is multiplied with the term 100 by 0.67 into 10 power 5, so the change in volume is equal to 469 cubic millimeters. So this is the change in volume of the bar. So like this, we have to evaluate the different problems, and we can find out the unknown quantity values with the given data. Now coming to the summary part. So in this class, we have discussed about the elastic constants like Young's modulus, modulus of rigidity, Buck modulus, Poisson ratio, that is ECK and 1 by M, and also we have discussed about the relation between the EC and K, and we have discussed about the volumetric strain. The volumetric strain EV is equal to the change in volume by original volume, that is delta V by V, and we also having the relation between the ECK and here, and with this, and we have solved some of the problems. Now we'll go to the quiz part. The relation between the Young's modulus and rigidity modulus, that is E and C. This is the correct one. E is equal to 2C into 1 minus 1 by M. Option B is E is equal to 2C into 1 plus 1 by M. E is equal to 3K into 1 minus 2 by M. E is equal to 3K into 1 plus 2 by M. Here, the option B is the correct answer. And the volumetric strain EV is given by the relation. Option A, change in volume by original volume. B, option B, lateral strain by linear strain. Option C, strain by stress. Option D, change in volume into original volume. So we know that the Volumetric strain is nothing but the change in the volume by original volume. That the option E is the correct one. And we got some problems, and by solving these problems, we're going to have the clear idea and clear knowledge about this volumetric strain. Now this is about the lesson on the volumetric strain. So thank you. I'm stopping my desktop sharing, and I'm ending this lesson. So once again, thank you all of you.